Okay, we're back and we're doing some circuits. And in particular, we're going to look at capacitors in series and parallel. Capacitors are those little devices that fundamentally store charge, and they also store energy. So just like resistors, you can hook them up in series and parallel when you have multiple capacitors. And we're trying to find out what the rules are for adding capacitors together. Now, just like what we do for resistors, we can hook them up in series and parallel, so we've got these Kirchhoff rules. The voltage rule is identical. It's really a fundamental rule that we have for any kind of circuit, where if you know what the input voltage is from a battery, as you work your way around the circuit, by the time you get back to the battery, all that voltage is used up. So if we have all capacitors, the sum of the voltages of each of the capacitors have to add up to the voltage of your battery. Now in parallel, similar to what we have for resistor circuits where the current breaks up, here we have the charge being stored is broken up across the branches, and charge is conserved. So if you add up the charges on all the branches, that should add up to the total charge of your circuit. And what we have for capacitors, a fundamental rule, is the charge on a capacitor is its capacitance, or how many farads it has, times the voltage that you have across it. Okay, so using these, we're going to find out what the rules are. Okay, so here's a series circuit with 3 different capacitors, and the voltage rule says that the voltage of your battery has to be equal to the voltage of those 3 capacitors. Okay, so using this Q equals CV relationship, we can basically try to figure out what's the voltage on each capacitor. Well, to do that, you also have to know what the charge is on the capacitor. And in series, it turns out that whatever your capacitance is doesn't really matter. You're going to have the same charge being stored. Very similar to resistor circuits, where no matter what your resistors are, you have the same amount of flowing charge, okay, current, moving through each of those. Here you have the same total charge, or static charge, being stored on each capacitor. Okay, so because that's the case, that charge is going to be the individual capacitance we're looking at voltages here, so the voltage across the first one is going to be that charge divided by C1. The second one has a voltage charge divided by C2, and then charge divided by C3. On the left hand side, your total voltage, that's equivalent to your total charge divided by your total capacitance. Now, because all these charges are the same in series, we're going to have our rule to find the total capacitance. Okay, you have to add up each of those, the reciprocals of all of these capacitances. And after you add those up, whatever that fraction is, we're going to have to flip it over. This is the same rule that we have for resistors, but when they're in parallel. Here, this is how you add up capacitors in series. If you took those same capacitors and hooked them up in parallel, the cool thing here is that, as we know, in parallel you have the same voltage across every branch. Now our rule is that your total charge, it's our Kirchhoff rule in parallel, is equal to the sum of the charges of each branch. Okay, so to find charge, we have Q equals CV. So the charge on capacitor 1 is capacitor 1 times whatever the voltage is of your battery. C2 times the voltage, and then C3 times the voltage. On the left hand side, this would be the same as saying, what's the total capacitance times the voltage of your battery? Now, because the voltages are all the same in parallel, those drop out. And we have our rule for capacitors in series. You just add them up. So we end up with the same two rules that we have for resistors, only they flip-flop. You add them up in parallel. That's the easy one for capacitors. But in series, you have to use that reciprocal rule. Add the reciprocals, okay, find that fraction and flip it over. Okay, so I hope this helps. I hope you can see how we can use these Kirchhoff rules in the context of capacitors and actually derive these rules to find the totals. Okay, so I hope this helps, and until next time, we'll see you later.